Hi everyone, we're the Automated Waste Segregation Group and we're proud to present our solution to litter and waste management. We designed an autonomous robot that navigates a room, picking up and sorting any litter into its respective category. My name is Nathan and I'm joined today by Shivang, Sean, and Zewa. So why did we decide to target this area? Well, every year lots of work is done by volunteers to pick up large amounts of litter from our streets. This process isn't sustainable as litter gets picked up by wind and cloud, getting scattered across the city and into water bodies. Any litter that is picked up, however, needs to be sorted appropriately, otherwise it ends up in landfills. We want to avoid landfill sites because they're terrible for the environment. They release large amounts of greenhouse gases while also polluting local soil and water. The main people affected by litter and waste management who would use our product would be municipal governments and companies in charge of cleaning littered areas such as beaches and parks. I will now pass it on to Sean and he will talk about our solution.
Thank you, Nathan. Here's a 3D model of the final design of the vehicle. This is the model of the chassis. The sidewalls, the red platform in front which shows the robotic arm, and the locks in grey were all 3D printed using ABS. The front wall and the floors were laser cut using PMMA. Due to dimensional limitations of the machining methods, we had to break down the floors and walls into smaller components, and design locks to hold them in place. Due to the speed of the vehicle being relatively low, these locks and parts were designed to be held together, mainly via friction fits and duct tape. Here are the rest of the components. Moving from left to right, we have the deep 5 degree of freedom robotic arm to pick up the objects. We then have the PI camera to recognize the type of object that's being picked up. Then we have the TOF sensor, which is the time of flight sensor, and this helps with the object tracking. Finally, in the bottom, we have the LiDAR to map the surrounding environment of the vehicle. I will now be handing over the presentation to the software team to discuss further how the system works.
Thank you, Sean. My name is Zihua. I will introduce the software system of our project. Our project contains two subsystems, the self-driving system and the object tracking system. The self-driving system uses LiDAR combined with low navigation pad and exploration pad to help the robot explore the surrounding environment. Simultaneously, the robot will use a camera with TensorFlow object detection API to find the target object. Once the robot finds the object tracking system will locate and track the object, then pick it up and place it into the selected bin. I will talk about self-driving system first, and later Xiaowang will cover the object tracking system. The self-driving system uses the LiDAR with hacked SLAM to create a map of the surrounding environment and locate the robot's position in the map. Then the low navigation pad will add the information into the map. The information is the blue area around the obstacle. It provides an extra space between the real robot and the obstacle to prevent potential collisions. The low navigation pad uses dice search algorithm to find a path from the current robot's position to the destination point. The path is indicated in green line in the map, but it's hard to see from this video. After we have the path, the local path planner, which indicated by this yellow area, will control the robot to follow the path and avoid the obstacle using trajectory rolled-out algorithm. The exploration package is used to set the destination point for the navigation path by identifying the frontier on the map. Frontiers are the edges that connect the known area and the unknown area, which indicated by this blue line here. By setting the destination point in the frontier, the robot will be able to explore the surrounding environment by itself. The video on the right shows our robot perform these self-driving systems, and next, Xiaowang will cover the object tracking system.
After mapping the room using SLAM and reaching the center of the room, the robot now begins to rotate about its own axis. During this rotation, the time of flight sensor looks for sharp, discontinuous changes in distance values. This is done using slope calculations. Once such a sharp change is found, the PI camera is triggered, which now uses its object detection model to verify the object, as can be seen on the top right images. Once this verification is done, the robot now begins to move towards the object, as can be seen in the video. The object considered in this case is the white tissue. This movement is done until the robot is a fixed distance apart from the object to be picked up. Once this distance is reached, the arm is now triggered to pick the object up and place it into the correct respective bin. It is important to note that for our project, the robotic arm could not reach the sorting platform. However, the object detection model was complete and working. As can be seen from the videos in the last two slides, we managed to get both the subsystems, the self-driving system and the object tracking system working independently. The state diagrams for each can be found on the left and right respectively. However, there is still a missing link. Due to the complexity of the project and the limited time we had, we could not integrate the self-driving system with the object tracking system. So even though both the systems work independently, the robot could not simultaneously explore the environment and search the target object using the camera and time of flight sensor. In a future iteration of the project, we will use the motion node to connect the self-driving system with the object tracking system. In such a manner, the robot could screen the environment while exploring its surroundings. Another issue is that we could not install the sorting platform correctly. This is because of the reach of the robotic arm, as well as the manufacturing variability. That is, parts of the sorting platform did not fit. Therefore, the sorting function is not complete. However, the object detection is correctly able to identify the respective category of waste. This project is a prototype or a proof of concept to show that it is possible to make a self-driving robot that can pick up garbage and sort it in an indoor environment using a time of flight sensor and a Raspberry Pi camera. However, by no means is this design perfect, and here are a few possible improvements. we could indeed connect the two systems, self-driving and object tracking acquisition, together in order to have a better final system. A final feedback loop could be incorporated for robustness of experiments, as well as the sorting platform could correctly be incorporated using a bigger robotic arm and with better manufacturing. Thank you.